To make fiber optic cables, manufacturers heat glass to 2000 degrees Celsius, hotter than the surface of the sun, and then stretch it thinner than a human hair. But here's what most people don't know. That's just the beginning of an insanely complicated process. Today, we're diving deep into the fascinating world of fiber optic cable production. At their core, fiber optic cables are incredibly simple yet sophisticated technology. Unlike traditional copper cables that transmit electrical signals, fiber optic cables use light to carry information. This fundamental difference allows for faster transmission speeds, higher bandwidth, and significantly less signal degradation over long distances. The magic happens inside the glass core of the fiber, which is thinner than a human hair. This core is where light travels, bouncing along the length of the cable through a process called total internal reflection. Surrounding this core is a glass cladding with a lower refractive index, which keeps the light contained within the core. This entire glass structure requires protective layering that transforms fragile glass into the durable cables we rely on every day. Creating fiber optic cables begins with extremely pure glass. Not just any glass will do. The manufacturing process starts with a specialized form of silica, silicon dioxide, that must be 99.99% pure. Even the slightest impurity can significantly affect the cable's performance. This ultra-pure silica is often supplemented with various dopants, chemicals added in precise amounts to alter the glass's properties. Common dopants include germanium dioxide, which increases the refractive index of the glass core, and fluorine, which is the industry standard for decreasing the refractive index in the cladding. While boron oxide can serve a similar purpose in specialized applications, fluorine is the dominant material in modern telecommunications fiber. These carefully selected dopants create the precise conditions needed for total internal reflection to occur, allowing light signals to travel efficiently through the fiber. The journey from raw materials to functional fiber begins with creating what's called a preform. This large, thick glass rod serves as the prototype for the final fiber. The preform must maintain the exact proportions between the core and cladding that will appear in the finished fiber, just on a much larger scale. Several methods exist for creating these preforms, but one of the most common is modified chemical vapor deposition, MCVD. In this process, gases like silicon tetrachloride and germanium tetrachloride are passed through a rotating tube made of synthetic quartz. A torch moving along the tube's exterior heats it to temperatures exceeding 1,600 degrees Celsius, reaching up to 1,800 degrees Celsius. At these extreme temperatures, the gases react to form fine particles of silica and germanium dioxide that deposit on the inner wall of the tube. Layer by layer, these deposits build up, with the concentration of dopants carefully controlled to create the desired refractive index profile. Once enough layers have been deposited, the tube is heated to an even higher temperature, causing it to collapse inward and form a solid glass rod, known as the preform. The precision required during this stage is extraordinary. The composition and geometry of the preform directly determine the optical properties of the final fiber, so manufacturers must maintain exacting standards throughout this process. Even minor variations can lead to significant differences in how efficiently the finished cable transmits light. With the preform complete, the next step is to transform this thick glass rod into the razor-thin optical fiber needed for telecommunications. This process, called drawing, is both simple in concept and remarkably complex in execution. The preform is loaded vertically into a drawing tower, a specialized structure that can reach several stories high. At the top of the tower, a furnace heats one end of the preform to approximately 2,000 degrees Celsius, 3,600 degrees Fahrenheit, softening the glass until it becomes malleable. Gravity then pulls the softened glass downward, causing it to thin dramatically as it descends through the tower. Now that the glass fiber optic strands have been created with their core and cladding perfectly aligned, the next critical step is to protect them. These delicate glass strands would fracture under installation stress without sophisticated protective systems. The protection process begins immediately after the drawing stage. The first layer of defense is the primary buffer coating, a UV curable acrylate, photopolymer, applied as a liquid. It is then rapidly cured by ultraviolet light while the fiber is still on the drawing tower. The coating serves two crucial purposes. It protects the glass from moisture and abrasion while also adding strength to the delicate fiber. But this single coating is just the beginning. Each successive layer serves a distinct purpose in creating the final cable design. Individual protected fibers are rarely used alone. Instead, they're bundled together in various configurations depending on the cable's intended use. The most common arrangement is the loose tube design. In this configuration, several coated fibers are placed inside a plastic tube filled with a special water-resistant gel. The gel not only provides additional protection against moisture, but also allows the fibers to move freely within the tube, reducing stress during installation and temperature changes. For higher fiber count cables, multiple loose tubes are arranged around a central strength member, typically made of steel or fiberglass. This central element bears the mechanical strain during installation, protecting the fragile optical fibers from excessive tension. The arrangement of these tubes around the central member creates what's known as the cable core. The cable core, while organized, still needs significant reinforcement to withstand the rigors of real-world use. This is where strength members come into play. Depending on the cable's intended application, materials like aramid yarn, better known by the brand name Kevlar, fiberglass rods, or steel wires are incorporated into the design. For cables that will be buried directly in the ground, steel tape armoring might be added. This forms a tough barrier that protects against crushing forces and rodent damage, a surprisingly common threat to underground cables. The outermost layer of the cable is the jacket, typically made from polyethylene, PVC, or other durable polymers. This final layer is crucial as it provides environmental protection against UV radiation, moisture, chemicals, and physical damage. The material used for the jacket varies depending on whether the cable will be installed underground, underwater, or suspended in the air. For outdoor applications, black polyethylene is often chosen for its excellent UV resistance and durability. Indoor cables might use PVC jackets that incorporate flame-retardant additives to meet building safety codes. Specialized applications, such as underwater cables, require even more robust designs with multiple layers of waterproofing and armor. Throughout the manufacturing process, the fiber optic cable undergoes rigorous testing to ensure it meets industry standards. These tests include optical testing to verify signal transmission capabilities, tensile strength testing to ensure the cable can withstand installation forces, water penetration testing to confirm waterproof properties, temperature cycling tests to simulate environmental conditions, crush resistance tests to ensure durability. Each completed cable is tested for optical performance, measuring parameters like attenuation, signal loss, and bandwidth. Only after passing these tests is the cable spooled onto large reels, ready for shipment and installation. The finished fiber optic cable represents an extraordinary achievement in materials engineering, a perfect marriage of delicate glass technology and robust protection systems that can survive decades in the harshest environments while faithfully transmitting billions of bits of data every second. The next time you stream a movie or make a video call, remember that your data is likely traveling through these remarkable cables, zipping along at the speed of light through microscopic strands of glass, protected by layers of engineering ingenuity. Thank you for watching another episode of Everyday Nuggets. If you enjoyed this episode, please like and subscribe for more videos. If you have suggestions for other everyday things you'd like to know about, please leave them in the comments below. Stay curious.